Okay, still better like that, sure. Doesn't matter much what kind of data it is, but we're trying to predict some value. We're not generating things, we're trying to predict whether somebody's gonna default, let's say, on their credit. And when we make that prediction, we want to kind of know whether this model is correct or not, roughly speaking, on general level. But if we make prediction far in the future, then we cannot just calculate the performance. We cannot compute our normal metrics like F1 or precision or your squared error of your model because you don't have the ground truth. So my presentation today is going to be about how we can get the expected value or the expectation of that machine learning performance, the quality of the predictions, without access to that ground truth. So let's get started with the agenda. And of course, the main reason why you want to do it is that if your model stops performing well in production, you might be losing a lot of money. Maybe your model is not making you money anymore, but it's losing money because it's no longer accurate. So we're going to talk about what are the reasons why this performance can actually drop once you deploy your models to production, once you start operating in the real world. And then we're going to talk about two algorithms we developed at NannyML. NannyML is an open source Python library. We also have a cloud version. I'm going to talk about it briefly later on. And we're going to talk about two algorithms that we've developed that allow you to estimate the performance of machine learning models without access to the ground truth. So right when you make the prediction, you'll be able to tell what is the likelihood that this group of prediction is correct or not, roughly speaking. And we're going to discuss these two algorithms. The first one for regression models, when we try to predict continuous value, is called direct loss estimation. And for classification models, it's called confidence-based performance estimation. So let's get started why this performance is actually important for your machine learning models. Yeah, so why do you even need to monitor machine learning models? Why can't you just deploy things and forget about them? And the reason is simple. When you deploy your model, you want to basically care about whether it's correct or not, because quality of the model directly translates to business impact of the model. If you can predict credit scores with 100% correctness all the time, then you're going to make your company billions. If you're as good as random, you're probably losing your company money. So when you develop the model, you're going to develop some kind of metric. Let's say it's precision, recall, or something. And you're going to use it as a proxy for the business impact that your model has. The higher the precision of the model, the higher is the impact. And when you deploy a model, we want to maintain that business impact. We want to make sure that our precisions, or generally speaking, performance metric, stay consistent in time. The second reason is we want to reduce the risk of the model, because models operate in the real world in either augmented systems or fully automated systems. They add additional level of risk. If they go wrong, you might start losing money or you might make less money because the models are not doing well, and that's additional risk. So by monitoring and providing full observability to your model in production, we're reducing that risk. And this third reason, kind of more on the personal level for you as a data scientist or machine learning engineer or head of machine learning engineering department, you want to increase the visibility of the model so other people know what is the impact that you make personally or as part of your team on the company, because that will bring more budget and potentially some raises. So these are the reasons why we need to monitor machine learning models. Now, how do we do it? The first step is to know the performance of your model. I already explained why it's important and why sometimes we cannot just measure it, so we need to try to estimate it. And only when we know that the performance is decreasing, we should look at potential reasons. One of the typical reasons is that your data, your input data, becomes different. Maybe you're mostly focused on clients in Germany, but now your company expanded to Austria or to France. And people that are different, they maybe are distributed differently, they react differently to your product, and the model might break. So if that happens and we see drop in performance, we should do root cause analysis. We should try to figure out what exactly went wrong. And once we know what went wrong, then we can proceed to issue resolution and actually try to resolve the problem via retraining the model or some other things. I'm not going to go too deep there because of time constraints. But retraining is not always the solution and will not always improve the performance of your model if certain things happen to the distribution of your data. And now we're going to slowly get more and more technical. So let's first start with performance monitoring specifically and Again, why it's important. It's a proxy for the business impact. It identifies potential issues. So there might be some issues in your data. Your data might drift if you have a few thousands of features. Let's say you use embeddings, and the embedding length or the embedding dimensionality is, let's say, 500. Some of these embeddings will definitely drift. The distribution of those embeddings will change, but that doesn't necessarily mean that the performance of your model is in any way impacted. So you only want to go into root cause analysis and look at all the embeddings if performance changes. So it's kind of a trigger for that root cause analysis. But again, as I mentioned, it's not easily possible without the target data. That's why we need to talk about performance estimation. Quick kind of decision tree or flowchart about how to do performance monitoring. It's very easy stuff. We start with the performance monitoring. We look whether our ground truth is available, whether we already know whether a person defaulted on a credit risk or on a credit or not. If yes, we can just calculate performance. If no, we need to do performance estimation. And here we get to kind of the core of today's presentation or workshop. And we have two algorithms for classification CBPE, for regression DLE. So we kind of covered the high-level view. What is the reason why we need to do performance monitoring? Now let's focus on what can actually happen once we deploy a model to production and what can go wrong. So there are two reasons why your models can fail silently in production. As I covered them, we need to get back to basics and, similarly to the previous presentation, talk about some high-level machine learning ideas. So when we train a supervised machine learning model, what we basically try to do is we take certain number of features, your model inputs, and we try to find how they map to your model output. Let's say that you try to predict whether somebody's going to default on a credit score or not. Here, let's say we have just one feature, feature X. And as this feature X increases in value, we see that the relative frequency of positive class, which is people defaulting on credit score, decreases in this kind of sigmoidal level. So let's say that this feature X might be H. As H increases, people are less likely to default on a loan. This is the true pattern that exists in the world. Now we're going to sample from that true pattern. We're going to get our data. This might be part of our customer base, maybe even all of our customer base, but it's not the entire population because we still have future customers to acquire. We have customers that we could have acquired, but we didn't. So we're going to sample and we'll get our data. And now when we train a model, we're going to use that data to try to find the pattern that exists in reality based on our sample. And we have a model. We finished training. But unfortunately, when we deploy our models to production, both the true pattern and the sampling mechanism might change, whether we want it or not. If the sampling mechanism changes, what we're going to see is so-called covariate shift. So the distribution of our features will change. And if distribution of our features will change, it will mean that the distribution of our data will change, and potentially the distribution of our target will also change. And if this data drifts to a region where the model is not performing well, for one reason or another, we're going to see a drop in performance. One reason why it might happen is that the model was not trained on the kind of data that we see now, so it had not enough data to capture the actual pattern that exists in the data. If that happens, you will not see good generalization performance and your model will silently fail. It will still predict something, it will look fine, but it's not actually going to be very correct. Another reason why your model can fail is, imagine that instead of drifting to the right here, drifting to the left here, it drifts to this side, whether it's left or right. And let's say it drifts to the region where it's basically 50-50. You don't know whether it's going to be a positive class or negative class. In that region, there is no information about the data that allows you to discern between positive and negative class. So the predictions will be random because the model has no information to use. So the performance will also decrease, not because the model did not learn the pattern, the model learned the pattern, but there is no meaningful pattern to learn there. So it's like basically tossing a coin. And if you see more data points from that region, the model performance will decrease. Just kind of, let's say, more scientific formulation of what covariate shift is. It is the change in the joint model input distribution, so the P of X, if you look at it from Bayesian perspective. That was also mentioned in the previous talk. Now, the second reason is concept drift. Concept drift is changed not in the sampling mechanism, but in the true pattern. So the actual pattern that we're trying to learn from the data has changed in time. That means that, of course, our data has changed, and that means that in general, almost always, the performance of our machine learning model will drop because the pattern that was there is no longer relevant, so we're going to mispredict on any data point where the pattern has changed significantly. But here, to really evaluate whether there is concept drift, you really need to have access to ground truth. So from now on, we're going to focus mostly on covariate shift and how it impacts performance, because we can say something about covariate shift even without ground truth, and we know that it impacts performance. Just again, formal definition is the change in the relationship between our mapping between the target and the model input. So it's the probability of y where y is ground truth given the x where x is the feature vector. Okay, and now we covered the basics from the perspective of what can go wrong. Now let's try to quantify and see if we can somehow map these things going wrong, covariate shift, to actual impact on model performance. And first, we're going to look at the regression models. So imagine that you have a regression model, you're trying to predict something. Let's say it's demand. So you predict number of units sold per given day, maybe number of bread pieces in a bakery. We're going to then measure the performance of that model. You have a number of traditional metrics that you can use, such as root mean squared error, mean absolute error, mean squared logarithmic error, and all the others. And these are the metrics that we can estimate with our algorithm. We can estimate anything that can be defined on an instance level. So if you can compute something like squared error, logarithmic error, we can use DLE to estimate those metrics. What does it do? It captures the full impact of covariate shift on performance. So one of the two reasons why the models can degrade in production, and it's actually the reason that happens more often because you have a lot of features normally. So there's almost some kind of covariate shift happening in reality. We assume that there is no concept drift because, again, we need to know the ground truth to really measure the concept drift in any meaningful way. And we assume that there is no covariate shift to regions that were not unseen, because then we cannot establish any kind of pattern between the covariate shift and performance. What does it take as inputs? So we're available, as I mentioned, in Python, open source, on GitHub, and you can just pip install us and use it as follows. We take the model predictions, so whatever our model predicts. We take the true values, so the targets, but only for the dataset for which we're going to train the model on. So we actually need to have a dataset for which we know that the performance was satisfactory. This is normally your test set. You test your model on your test set, you see that the performance is fine, you have ground truth there, you know that everything is okay. And we're going to use that test set again to train the model that will try to map the model predictions and the features, the model inputs, into the expected performance. So we're going to try to find the regions where the model is not going to perform well, and we're going to try to find regions where the model is performing well. And then we're going to use that model that we just trained on our production data, on our analysis data, and then we're going to try to see what is the expected level of performance there. So we take the predictions, we take the targets for our test set, we define which metrics we want to use, and then we take all the model inputs, so the features, as additional input. What does it output? It outputs three things. The actual metric, so let's say we have MSE here, and we see what is the evolution of MSE in time as we deployed our model to production. The left side is the reference data or our test data, and the right side is the, doing it the other way around. It's the right side for your. So we see the analysis data on your right, my left, and basically you get that the MSE is increasing in time in this example. We also get confidence bands, which is the region where the actual true performance is very likely to lie based on the sample of our data. And you have the threshold of acceptable performance, which is by default calculated based on the variability of the data in our reference data, but it's a threshold that you might change based on business requirements. If you can accept average MSE up to 10,000, you can set it to 10,000. If you don't know what's acceptable, then it will just be automatically established based on variance. And one thing that we see normally is people say that it's impossible because you already use all the available information in the data to predict the actual ground truth to get the best possible point prediction. And turns out that the two problems of trying to predict the performance and trying to predict the point prediction as well as possible are actually slightly orthogonal, or in some cases even fully orthogonal. And I'm going to try to build the intuition for that here. So imagine that you have a very simple model that just takes feature one feature, and based on that tries to predict the target. And we see that there is some kind of linear relationship. If feature 1 increases, the value of the target also increases. So we train a model, can be linear regression, can be LGBM, you can build embeddings if you want, although there's obviously no reason, and you get some kind of point prediction. But you also see that there is a different kind of relationship here, that as feature 1 increases, the dispersion of the target also increases. So on the left side, the target is very concentrated, on the right side, the target is very dispersed. And if you look at the expected difference between the pink line and the data points, this is kind of your error. This is your squared error that you calculate. And you can also estimate what is this expected error or expected loss, to be more correct here, between the pink line and the actual values. And you can just train another model that will calculate this estimated loss, because you can calculate this estimated loss for any given point. You will find a pattern that it increases as feature 1 increases, and that's what you get. You get the output, which is basically this estimated loss. To build this intuition a bit further on another example, imagine here we have two features and we're trying to predict some continuous value. We have feature 1, feature 2, and we're able to, for every data point in this input space, we're able to calculate the expected squared error or realized squared error on the test set. So for every data point in the test set, we calculate squared error between prediction and the target value. And then we plot it as this kind of heat map, where if you have low realized squared error, then it means that the model is very confident in its predictions, or is very certain about its predictions. And we see some kind of data distribution of our points. And as we deploy models to production, we experience covariate shift. This distribution changes. And we see that there is more points in the regions where we expect to see high squared errors. If we expect to see high squared errors for more points, then on average, we're also going to see higher expected squared error, which means that our metric, let's say mean squared error, is going to increase. And that's it. That's the intuition. And it basically means that actually we can kind of treat the model performance and actual best predictions as two disjoint problems, because they use different kind of information. That's the intuition. I hope you got it. Otherwise, there's always time for questions. Now let's go into the actual algorithm, just to give you a quick overview of how the algorithm works. First, we're going to calculate this loss metric on the reference data. So we calculate the squared error on every point in our reference data, which is our test set. Then we're going to train a model to estimate this loss metric, because why not? We can, using the model input features and the actual model predictions from the model that we monitor, the one that gives you point predictions. And then we're going to directly estimate this loss on the analysis data. That's the whole algorithm. We just train another model to estimate uncertainty of the previous model. And it works in practice. Now, we're going to move to the second part, which is confidence-based performance estimation. So how do we do the same thing on the classification models? And here we can be a tiny bit smarter, but first let me go through the same steps of how, what we can do, what does it take, what does it output, and how does it work. So what we can calculate. Here we're going to again be able to calculate basically any traditional machine learning metric or performance metric for classification models. So we can calculate anything that has to do with confusion matrix. I'm going to use binary classification here as an example, but we also support multi-class classification, and you can compute multi-class classification confusion matrix as well. We can compute precision, recall, accuracy, specificity, F1, any metric that stems from the confusion matrix. And we can also compute ROKUC, which is good measure for, how do you call it? The predictive power of the algorithm. What does it do? The exact same thing, so we can go fast through that. It captures the full impact of covariance shift on performance, no concept drift, and no covariance shift to previously unseen regions. The inputs are quite similar to DLE, but can be, as I mentioned, we can be a bit smarter here. So instead of taking just the predictions, the targets, and the model inputs, we're not gonna take model inputs here. And instead of model inputs, we already have a measure of uncertainty of the model. For regression models, we only got point prediction. We didn't get any information about how certain the model is about its prediction. Here, we actually have it. It's the predicted probabilities. Almost all classification models return some kind of form of predicted probability. Unfortunately, this is not true predicted probability. It's just a value between 0 and 1 that doesn't really fulfill the definition of probability. More on that in a second. And we need to specify whether classification is binary or multi-class, but that's just for engineering needs and how we structure the library. So we have those. We're going to, again, fit the model on our test data, and then we're going to use that model to estimate or predict the performance on our production data for which we have no labels. The results, again, the same as before. We're going to have a metric normally between 0 and 1 here, confidence bands, thresholds, and the actual performance prediction. The intuition. We're going to go at the intuition again. The intuition is quite similar, but I find it that it's easier to understand, at least for me, when it's presented for classification models, because they generally tend to have a similar shape that's easy to understand. So imagine we have, again, test data or reference data. We have some data points, and we are able to measure the predicted probability of the model. Just take the predicted probability, and we plot it as a heat map. Maybe we're going to fit some nice KDE around it so it looks pretty, and we get this beautiful butterfly shape. And what you see is that on the right-hand side, one of the wings of the butterfly is class 1. That's where most data points from class 1 are. The model is going to be very confident that this is class 1 because it's very simple to distinguish. There's basically no points that belong there to class 0. And the same is true in inverse for the left wing. There, all the data points belong to class 0, so we also have very high model confidence. The model says that the prediction is 0.001, almost certain it's class 0. And then we have this region in between the body of the butterfly where we are not sure. This is the class boundary. Here the model can predict 0, 1, it's going to predict 0.5, 0.55. It's really not sure whether this is class 0 or class 1. Just because here there is a lot of data points both from class 0 and class 1. There's a lot of overlap, the data is not linearly separable. And then we deploy the model to production, and for one reason or the other, our data points drift closer to the class boundary. So the model confidence will decrease, so the expected performance will also decrease. That's the intuition. Hopefully this time it was slightly easier to follow. And now let's follow on with the model recipe, so the actual algorithm. And here it's slightly different. So first step, we're going to calibrate probabilities. So I mentioned that the probabilities are actually not real probabilities. They are just numbers between 0 and 1. And we have to turn those numbers between 0 and 1 into actual probabilities that follow the definition of frequentist probability. Then we're going to choose a threshold. We're going to choose a number between 0 and 1. And we're going to take the threshold that we've chosen when we developed our use case to turn those probabilities into an actual prediction. We're going to find the expected confusion matrix for every element. So we're going to, for every data point separately, we're going to construct like a mini confusion matrix. And then we're going to use it to get the aggregate confusion matrix for a number of data points. So we're going to batch our data together. And then we can compute a metric such as F1. Let's go through it step by step this time. So first thing is probability calibration. So what we're going to do here is we're going to take the mean predicted probability. So we're going to batch our data, first sort our data by predicted probabilities in the test data, and then we're going to batch it into buckets. So we're going to bucket our data actually. Values, let's say, in 10 buckets, 20 buckets, whatever it is. And then for each of these buckets, we're going to measure what is the fraction of realized positives in the test data. So ideally, if the model is well calibrated, if we look at the bucket where the mean predicted probability is 0.5, we would expect 50% of those data points to actually turn out to be positive. But this is unfortunately not true for almost any model. Anything that's based on deep learning, including also LLMs obviously, or computer vision models, or NLP models, or graph neural networks, anything is not going to output a straight line. If you work with anything that uses model ensembles or decision trees, you're going to have this S-shaped line. If you use SVC or any kind of support vector models, it's not gonna output a straight line. If you use Bayesian neural networks or Bayesian learning, it's also not gonna output straight line. Only linear models actually output straight line. So we're gonna straighten this line. Make sure it actually, when we say 0.3 predict probability, it actually means that there's 30% chance that the model is gonna output 1. We're gonna do it by fitting a regression model on that. That's the simple solution. And then, on average, in the aggregate, if we look at the entire population at once, and with a big enough batch, we actually can say that this predicted probability corresponds to real probability. So we take that predicted probability, we use some kind of threshold, and we got some kind of prediction. Then, because we know that this predicted probability in the limit for the whole batch is true, actually corresponds to 90%, we can say that this is a positive class because we observed that the model returned positive prediction, and we can say that 90% chance that it's a true positive and 10% chance that it's a false positive because we know that the probability is correct. And we're going to do that for all the points in our current batch, maybe last 1,000 predictions, maybe last day of data, maybe last week of data, maybe last 1 million predictions, whatever is the volume of your use case. And we're going to do it for all of those. And we're going to compute this partial confusion matrix. Well, in true positive value, we put 0.9. We know it's not a negative prediction, so 0 goes there. False positive is 0.1, because we know that there's 10% chance it's actually a false positive, and we know it's not a false negative. We do it for all those predictions. And then we just sum it. And what we get at the end is we actually know what is the expected confusion matrix value for a given batch of data, taking into account the new distribution of the data. So taking into account covariate shift, which we explained can actually impact model performance. And we just take that, and from that, just like you would do normally, we compute F1, precision, and recall, whatever it is that you need to do. And that is really it. So thanks for listening. We are an open source company. Again, give us a star.
Thanks for the presentation. Just to make sure I understood what this is what's going on here. So DLE and CBPE, what is basically happening is that it's somehow calculating the sensitivity of a model to the feature vector such that it can estimate the performance of the model given the feature vector. So
yeah,
for a new feature vector that may have not been seen in the training data or the test data, or like in production, this model would be predict the performance of the model on such feature set. So basically, like a practical use case would be if you have multiple models and you have some kind of proxy in front of the models, and you can say, oh, this feature is going to get the most likely accurate prediction from model 1. I send it to model 1. If not, then I send it to model 2.
So the first part, I think it's precisely correct. Instead of sensitivity, maybe I would use uncertainty. So
Yeah.
So it can actually quantify the uncertainty of the model for any point in the vector space, in the model input space. And the typical practical use case is that if you deploy a model and the model makes a prediction and you don't get instant feedback about whether this prediction was correct or not, which is the case for almost all the use cases, except maybe high-frequency trading, where you get instant feedback, you basically want to know what is the level of the performance of your model. Is it acceptable? Does it still make enough money? Does it expose my business to a risk? And that performance estimation really allows you to answer that question with a simple yes or no. If it's a no, if everything is fine, then you continue operating as normal, there's no incidents. If there is an incident and your performance drops, that means that we need to trigger some kind of way to find out what's going on exactly. And we also have a set of features for that. But again, for time reasons, I'm not covering those.
Okay, I'm missing the part of why, if I did this, why wouldn't I leverage this as an additional dimension in my training data so that I can actually improve the model during training?
Okay, so that part is kind of what I talked about when I was building the intuition, which is all the information that will help you predict the actual target is already in your model inputs. It's already extracted from your model inputs, and it's already used by the model to predict the actual target. The model that we train only extracts different kind of information, right?
Understand this part. This information that you said that it's different.
Yeah.
Where do you break this information? Because let's say you have 3 features and you are estimating the target, right?
Mm-hmm.
And now, so my model did the exact same things, and now you're saying that the model that you train needs more information. Where this information?
So it's not more information. It's an information that's useful to a different thing. It's like trying to predict, to build an analogy. It's like trying to predict whether a picture contains a pig.
How's it going?
And then you're trying to predict whether this picture is sunny. These are actually 2 slightly different tasks. And we don't need the exact same information. And you can predict whether a picture is a pig, and then build another model that will predict whether it's sunny.
So in this case, the only things which is changed is the target, but not the actual.
Yes, so we're not predicting the target, we're predicting the uncertainty of the target.
But
Yeah.
we are using the same set of the feature for predicting the different things.
Plus,
Yes,
plus
exactly. We're using the same features, we're using the same information, but we're predicting 2 different things. Point prediction and the uncertainty around the point prediction, which we express then in performance metric.
Wait, I thought you actually take the predictions
As well.
produced by the
Yes,
model, right?
but we only take
so
the-
they're not taking this takes the prediction of the model and the target and the feature vector to estimate the confidence or uncertainty
model, yes.
So that didn't exist. Like that didn't exist in the training data. Did I understand it right?
We take it from the test set,
Yeah.
but the target, the thing that we predict is different.
But what I'm saying is, if we do this like
Yeah.
pre-production and then take the output
Yeah.
and then stretch the feature vector,
Adding this output.
yeah, and then train the model again, then the model would actually know that this is, would be able to estimate this for itself.
What do you mean by would be able to estimate by itself?
So if the model, like if we expand,
So I'm afraid we'll have to take that conversation offline because
Okay,
we're
maybe,
out. So
okay.
maybe like let's do 1 more 2 questions and then move on.
I'm really sorry. Let's
Okay.
do the questions after the last session. We'll still have time to.
yeah, no, thank you very much.
And thank you so much.
So now we're gonna go for the last session. Hi, Nick.
Hello, Jakob. Okay.
Hi, Nick. I'm sorry you cannot see the crowd. You're gonna see me, but the crowd sees you on a big screen.
Okay. Hello, everyone. Hello. Oh, I hear them. Wonderful. That was my question was, am I going to be able to hear people ask questions?
Yeah, you will. If not, I will translate it. But so with no further ado, Nick, the stage is yours.
All right, marvelous. All right, so let's go. Let's get going. I know it's really late for all of you over there. So what I'm going to do is I'm going to get through as much as I can in a reasonable period of time, and then I think what we'll do is we'll do a fuller session, where we really deeper dive. This is supposed to be a deep dive. We'll do a deeper dive, and you can all join me for that. So let me go ahead and share my screen now. So as we were saying, so today we are going to talk about retrieval augmented generation, or RAG. This is the thing that everybody's talking about. So what we're going to do is we're going to talk about what it is and how it works. So very quickly, who am I? I'm the Senior Director of Product Management and the head of the AI practice here at Cloudgeometry. I'm also the author of Machine Learning for Mere Mortals. That is what I do. I take complicated topics and I turn them into something you don't need a PhD to understand. So hopefully that's what I'm going to do here today. I know Annie also talked about the LFAI and Generative AI Commons. I also work with the Models and Data and Education and Outreach work streams, helping to co-lead those, and I represent the commons to the FinOS Open Financial LLM work group. All right, so let's talk about what we're going to talk about here today. So as I said, we're going to talk about what RAG is and why it matters, why you should care. And then we're going to talk about how does it actually work, because it doesn't do any good if you don't understand what's going on behind the scenes. Then we'll look at actual coding of it, not a toy example, but real stuff. And then hopefully we'll have time to get into sort of more of the optimization and tuning aspects of it to get better results, even better results, I should say, because RAG immediately is going to give you better results. All right, so what is it? Why you should care? So let's start out with a plain old LLM. So in this case, user asks a general question, LLM processes the question, it goes through all of these things that it knows based on all the data that it's been fed, and it gives you a literate answer that sounds like a human put it together. Great, that's terrific, that's what it's supposed to do. But sometimes, if you have a more specialized question, maybe not so much. So the LLM might process the question, it doesn't find an answer, and then maybe it says it doesn't know the answer, or maybe it gives you a hallucination. And in case you're wondering, I was wondering about this, why do they call them hallucinations? They're things that the LLM is absolutely sure of that are completely fictional. They're just not correct. So hallucinations are what we're trying to avoid. So what if we could provide extra information in this kind of middle step? So the user asks a specialized question, we do some pre-work to help find an answer, and then we let the LLM synthesize a result to give us that literate answer that sounded like it came from a human being, like we were talking about before. That right there, that is what RAG is all about. It's that center piece. And the reason that we use it is we want to get better answers. And there are lots and lots of use cases where this comes in. So, the simplest thing would be something like fine-tuning answers, just to get a better answer to the data, to the question that was asked. Or in the case of very specialized questions. Sometimes you really need to do something complicated in order to get the right answer. You could even insert an agent into that process. There's specialized information that you're giving back, like code generation or language translation. These are times where you may not want to rely on the statistical things that the LLM does to give you a result. Sometimes it's a matter of you want to give it specific information to act on. For example, you might have an LLM that understands medicine, it understands treatments, it understands diseases, but in that intermediate step, you might give it a patient's specific medical history and test results, and then feed that into the LLM, which could then give back treatment recommendations that are specific to that person. It would be the same thing for personalized recommendations. These are things that are specific to that person. So there's a lot of different ways that you can use RAG, a lot of different reasons that you might want to use it. So the question is, how does it actually work? It's great that you can do it, but how do you do it? So I'm going to thank Bill Williams for this very simple toy example. So imagine for a moment that you have a corpus of documents. We're just going to look at the pre-work section here for a second. Forget about the LLM. So let's say we have just a collection of suggestions for activities of things that you can do. And all you want to do is you want to ask the user, what's a leisure activity that you like? In this case, well, I like to hike. And it's going to go ahead and say, all right, I want to get a return response, which is going to basically compare this user input to the different documents using a function of similarity. The actual function here is irrelevant to what we're doing. But the important point is we're saying, all right, let's find the most similar thing and return it. So if we were to go ahead and say, all right, now I've got that code set up here. So here's my list of documents. I know this is a little bit hard to read. I apologize. And I'm going to say, all right, I like to exercise. If I went ahead and ran that, so I'm going to come over here. I'm going to say, all right, Python manual. Well, if you like to exercise, take a leisurely walk in the park and enjoy the fresh air. That is the actual sentence that we had in the corpus. That's great. Terrific. Easy enough. Now, let's say we want to go ahead and integrate this with an actual large language model. All right, so we say, all right, we're going to take some requests. We're going to use some JSON. This ellipsis here is the code that we already had for the most part. So we've got your prompt, your leisure, what's the leisure activity that you like. We've got the user input. In this case, it says, I like new things. We'll look at the code and see what it actually says. But what we're doing is we're saying, okay, we can get back that document that we got before, the document being the sentence. But before we actually send back a response, we're going to build a prompt that we are then going to send to the large language model. So here's the prompt. You're a bot that makes recommendations for activities. You answer in very short sentences and don't include extra information. Whoop. This is the recommended activity. That's what got returned in the last step. The user input is, and then compile a recommendation to the user based on the recommended activity and the user input. So the LLM is synthesizing this information based on all of its knowledge. So in my case, I'm just using Ollama to run Llama 2 on my laptop. So we're not doing anything fancy. We're just incorporating that information into the prompt, and then we're sending the prompt off to the LLM and getting a response back and printing out the response. So let's see what happens when we do that. I've got all my code, and let's see. It's the user input in this case is I like to exercise. So let's see what happens when we run it. Come back over here. Python manual LLM.py. It's going to take a few extra seconds because it's loading up the large language model and it's doing all of that processing. So there we go. So we have, so now we have our prompt. So we got back our original recommendation, take a leisurely walk in the park. Now, here's what we got back from the large language model. Sure, here's a recommendation for the user based on their input. Consider incorporating your love of exercise into your walk by adding some light jogging or jumping jacks into your route. This will not only make the walk more enjoyable, but also provide additional benefits for your physical health. All of that came from the LLM. And we were able to get that because we were able to provide it with that additional information. So if we go, that right here, that pre-work to find that answer to feed to the LLM, that is the heart of retrieval augmented generation, okay? Right in here, that's step 2. So what can you do there? Well, you can literally do anything. You can put in something that, you can put in one of those talk with PDF sections. You could read from a SQL database. So for example, you could have a SQL database that has order status, that you could pull the user's order status and then have the LLM have a conversation about the order. You could read from a vector database. If you're here, I don't need to explain to you what a vector database is. You can follow business rules, etc. You can call out to an API, to another system to find out other information. You can introduce a full-blown agent, as I was saying before. You can do anything in that step. It doesn't, there was no restriction on what you can do in that sort of pre-work step. Now, that was kind of a toy example, what we saw before. So fortunately, if you're going to do this for real, you do not have to code this by hand. Okay, there are lots of tools out there. Some of the most commonly known are Llama Index, LangChain. I'm going to show you Llama Index here just because I just picked one and that was the one. Again, I'm running Ollama on my machine so that I can run Llama 2. By default, Llama Index uses OpenAPI, so I'm going to say, no, don't do that. Use Llama 2, and we're going to use a local embedding because everything is here on my laptop. And then all we're doing is we're saying, all right, I want you to read all the files that are in the data directory. I want you to load all that data and create this corpus of documents. And then I want you to create a vector store index from those documents. Okay, so this is a fairly complex thing that we're doing, and we're doing it with just a couple of lines of code, which is great. Then we're creating a query engine from that index, and then we can send a query directly in. So I just made up a nonsensical thing. I said, all right, well, what color is the diamond baseball? Okay, there's no such thing as a diamond baseball. I just made it up. So let's see what happens if we go ahead and we try and do this. Now, in my data directory, all I have is one empty document. There's nothing in doc1.txt. I just had to have a directory there. So if I say, all right, Python app.py, because that's where the code is. I already loaded up. I loaded this up a little bit earlier so I could pre-warm it so you didn't have to wait for a couple of minutes while it, downloaded everything and ran everything. But it's still going to take a few seconds because, Llama 2 is not small. But it'll give us back a result in a minute. So it says the diamond baseball is purple. Okay, well, there is no such thing as a diamond baseball. Okay, if I ran it again, let's see what it says. Okay, it's just guessing at this point. Because again, there is no such thing. So we'll give it a few more seconds. And of course, when you have a whole crowd of people looking at you, time just expands, doesn't it? So while we're waiting, did you guys have a good day? Oh my goodness gracious, it timed out. So what's that? Well, I couldn't hear what you said. I hope you said you had a good day. All right. Good. Well, now it says the diamond baseball is blue. Obviously, it can't be all of those things. So let's go ahead and I have a file here, vi data1.txt, about the diamond baseball. So let's go ahead. I want to say the thing is the diamond baseball is, let's say it's green. Okay. All right. Now, and then I'm going to go ahead and I'm going to move data 1 to the data directory. All right. Now, let's try running this again and see what happens. So now I'm going to run it.
It's a very long time to figure out the color of the baseball.
What was that, Yakov? Can you repeat that? I couldn't hear it.
Yeah, it is a very long time to figure the color of
and get it wrong.
That's true. And actually, and it still got it wrong, actually. Well, that's the first time that's happened. There we go. The diamond baseball is green. Now, here's an interesting thing to keep in mind when you do this. If you're not careful, you will be training the language model. Well, that's interesting that it's now it's screwing up. The demo, apparently the demo demons have gotten me. But you can inadvertently wind up training your large language model. So for example, I ran this many times in putting this whole thing together. And then the large language model kept giving me back the value that I had given it even after I took the data away. All right, so let's go back to what we're doing here. So this was a very, very simple way to do this. But you have a lot of control over the parameters that you use, which is great because you can optimize and tune this as much as you want. I'm going to run through these very quickly because I know that I'm keeping you from drinks and socializing, and I wouldn't want to do that. All right, so some things that you can do on the back end, you can look at the sort of chunk size. So for example, you can break it out by sentences or, by 4-word tokens or whatever. The smaller the chunks, better for question answering because you get a more specific context. For summarization, you would want more like larger chunks. You can also do things like overlapping the chunks, as you can see here with the sort of gray here to get better context. The idea is to get just the right amount of context in it. You can play around with the embedding model, make sure that the data that you have is most appropriate to the model that you're using. Some can be fine-tuned, some cannot. In general, the higher the dimensionality in your embedding model, the better, but again, depends on your data. You can add metadata. So for example, in addition to adding all of your documents into a vector store, you might also add things like, the date or a file name or something like that that you could then filter on later to help you get a better result. You can use different indexing strategies. For example, you could create multiple indexes in order to get a better result for different searches. Instead of using k-nearest neighbor, maybe you want to use approximate nearest neighbor. There's a bunch of different algorithms that you can use. You can use what they call small to big. So you might find the relevant chunk to the answer to the specific question that you're answering and then sort of move outwards. So for example, you might find the sentence where the text appears, but you're looking for a much larger question. So then maybe you move out to the paragraph where the sentence appears, or even the chapter or book where that appears. So that's another way to get better context. You can also do what they call re-ranking. Similarity is not always the best way to judge relevance, particularly when there are, negatives involved. So if I say something like, what's the best way for me to not fall on the ice? If it's giving me instructions for fall on the ice, that would not be good. Also, when you do re-ranking, you get around a weird problem called lost in the middle. With these large language models, a weird thing that happens is that the items at the beginning of the list and the items at the end of the list get more attention and the items in the middle of the list don't. So while normal human ranking would say, give me the best at the top, the worst at the bottom, in this case, actually you want the worst in the middle because you don't want to see those. So that helps to get rid of some of these garbage responses. But the best thing that you can do probably is query transformations, because remember, what you're doing is you are creating a prompt that goes into the large language model. So you can do things like rephrasing the prompt. You can even feed the original question to the large language model to get a better prompt. You can create subqueries out of the original prompt. the hypothetical document embeddings. These are things where you sort of ask a question and then you get back a bunch of documents and then you use those documents to ask better questions and so on. But it's all a matter of prompt engineering to sort of give you the best answer. All right, so that was a very brief look at all of that. I'm 1 minute over what I said I would be, but anybody who's interested in a deeper dive, feel free to send me an email, nchase@cloudgeometry.io. I think we're probably going to put something together and we will get you information on it. Do we want to do questions or just to have people send me questions, Yakov?
So you can stop sharing your screen so people actually will see you.
Okay.
Cool.
Stop.
Hello, my name is Jonathan. I work for Wikimedia. We're building a RAG ourselves. I'm curious if all the code you're working on stores or runs the llama and the embeddings locally. And my statement is, do you have like an A100 or are you 4-bit quantizing the models? Like what's the process behind the scenes?
I don't. No. I'm actually running this on. I'm actually running this on a bog standard no GPU. Well, it does have 64 gig of RAM. It's just plain old, HP laptop. That's it. Nothing special. I thought I wasn't going to be able to do it, but Llama makes it very simple.
So we're asking now if it's Llama 7.
It's Llama 7.
Llama 7.
The size of the model. The size.
Oh, the size. Yeah. It's Llama 7. It's 7B. Yes. It's Llama 7B. Yes. I wish I could too, but thank you all very much, and have a great time drinking and socializing.